Last episode we discussed p-values, the determinant of statistical significance. But what does significance even mean? That's the topic of this module in analysis and reporting. Significance is so important that we need to go deeper than just p-values. Many times what we care about is, as Felix Schomburg says, and I'm quoting, what's the probability that a significant p-value indicates a true effect? In other words, what is the positive predictive value of a significant p-value? Another way of saying this, given that a p-value is significant, what's the probability that it stems from a real effect? We can look at this another way. Let's say that in 1,000 studies of different tests, we have 200 tests with a real effect and 800 studies with no effect. If we set our type 1 error, or alpha, to 0.05, then of the 800 tests with no effect, 95% were true negative studies, and 5% were negative effects with significant results or false positives. Let's further stipulate that we assigned a power of 80%, which is pretty standard in health studies. Then of the 200 real effects, 80% or 160 were true positive studies, but 20% or 40 are false negative results. These were real effects that showed up as not significant. Recognize, therefore, that of the 200 studies with a significant result, true positives plus false negatives, 40 were non-significant. This means that a full 20% of the significant results were not true effects. The false detection rate wasn't 5%, it was 20%. The positive predictive value, or the chance that a p-value of 0.05 means that it's true, was only 80%. Moreover, this was when we set power to 80%, which you probably should. Lots of people are willing to settle for less. The average power in psychology studies has been estimated to be 35%. In neuroscience, it's been estimated to be only 21%, and those are published effect sizes, which are more likely to be inflated because we're more likely to publish significant results. If we assume a 25% power with the same example I gave before with the 1,000 tests, then a p equals 0.05 yields 100 true positives and 80 false positives. The false discovery rate climbs to 44.4%, nowhere near 5%. This should blow your mind. If not, you're not paying attention. It gets worse. This assumes that every scientist in the study is totally acting properly and according to the processes and goals we've laid out in previous episodes. That's not always the case. Sometimes scientists engage in what we call p-hacking. Some researchers use questionable practices to push nearly significant findings over the p equals 0.05 threshold. Sometimes this is done unintentionally, but sometimes it's intentional. Even if we go back to 80% power, which is good, if just 15% of studies are p-hacked, then the false discovery rate goes up to 48.1%. This means that almost half of studies with a p-value of 0.05 are false positives. Half! No wonder so much research isn't reproducible. Lest you think I'm making these numbers up, John Ioannidis, a tireless crusader against flawed interpretation of research, reviewed the literature and published a seminal paper in 2005 entitled Why Most Published Research Findings Are False. That's where I'm getting all these numbers. If we look only at adequately powered randomized controlled trials with little bias and true equipoise, 1-to-1 pre-study odds of being correct, then the false discovery rate with a p-value of 0.05 is 15%. Confirmatory meta-analyses, which gather together good quality randomized controlled trials, have a false discovery rate of 14.6%. And these are the best case scenarios. Meta-analyses of small inconclusive studies have a false discovery rate of 59.4%. More significant results are wrong than right. Ioannidis found that an underpowered but well-performed phase 1 or 2 randomized controlled trial has a false discovery rate of 76.5%. A significant result at p equals 0.05 is 3 times more likely to still be wrong than right. An underpowered but poorly performed phase 1 or 2 randomized controlled trial has a false discovery rate of 82.5%, more than 4 times as likely to be wrong than right. Moreover, Ioannidis argues that exploratory research using massive databases is just a fishing expedition. If we're testing 30,000 genes and expect 30 might be significant, then the false discovery rate can be expected to be 99.9%. Sure, the p-value is 0.05, but that doesn't mean it's right. More than almost any other episode, this one is key to reproducibility. It gets at the fact that too often in research, we assume that p equals 0.05 or statistical significance means it's a slam dunk. That's not true. We have to get past that. Even results that meet the threshold of p equals 0.05 need to be retested again and again to make sure that they're correct. You need to remember that, from last episode, the p-value isn't the probability of being right. It's the probability of getting a value at least as extreme as observed, assuming the null hypothesis is true. Factoring in other data can help us to determine if a p-value is likely to mean a true positive result. That's almost always much, much less likely than people assume. Experiments need to be replicable. Results need to be confirmed. Just saying p equals 0.05 isn't even close to enough. When we assume it is, we get into trouble. This training module is part of a series funded by the National Institutes of Health.